So let's talk about Noether's theorem.
Noether's theorem, what a gem. In a nutshell, it's this beautiful bridge between symmetries and conservation laws. If your system behaves the same way under some transformation, say it looks identical if you shift it in time or rotate it in space, then voila, you get a conserved quantity. Time symmetry, you get energy conservation. Spatial symmetry, momentum conservation. It's one of those elegant truths that tie physics up in a nice, neat bow.
So what about you mentioned about two things, why time or rotate in the space? Why not other things? Do they include other things also?
Absolutely. It's not just time or spatial rotations. Noether's theorem applies to any continuous symmetry. If you have, say, symmetry under spatial translations, you get momentum conservation. If your system is invariant under rotations about an axis, angular momentum is conserved. Gauge symmetries in electromagnetism, that gives you charge conservation. Every continuous symmetry of the action leads to a conservation law. It's as broad as the symmetries you can define.
So you are mentioning about this symmetries and what do you mean by this continuous symmetry? Can you support your statement?
When I say continuous symmetry, I mean a transformation you can do in infinitely small steps. Think about rotating a circle. You can rotate by 1 degree, half a degree, a millionth of a degree. It's smooth and continuous. Time translation is another one. Moving forward by any tiny increment is still a symmetry. In contrast, a discrete symmetry might be something like flipping a shape. There's no gradual flip. Noether's theorem works with these continuous symmetries because they tie directly to smooth differentiable transformations.
So symmetries are okay. So can you give example in classical mechanics one and in quantum mechanics one where we use these Noether's theorems and understand the analog like how the intuition came and how these Noether's theorems works and help us to make our physics beautiful.
In classical mechanics, take a simple case, a particle moving without any external force in empty space. The laws don't change if you shift the particle's position. That symmetry under translation means momentum is conserved. Similarly, if nothing changes when you shift in time, energy is conserved. In quantum mechanics, consider a particle in a spherically symmetric potential, like the hydrogen atom. Because the system looks the same in all directions, angular momentum is conserved. Noether's theorem gives us a unified viewpoint. Every symmetry you spot, whether classical or quantum, guarantees a conserved quantity. It makes physics beautiful because it reveals deep hidden order. Symmetry is like nature's signature, and Noether's theorem helps us read it.
So, why you mentioned about this particle moving without an external force in an empty space? That's a more like a inertia condition.
Exactly. That's a classic inertial scenario. In an inertial frame with no external forces acting, the laws of physics don't prefer any particular location or time. That symmetry under shifts in position gives you momentum conservation, and symmetry under shifts in time gives you energy conservation. So, yes, when there's no outside influence, that's where Noether's theorem shines in showing how symmetry locks in these conservation laws.
That's a elegant thought. So you are telling that without any external force or something, we can, if we rotate the system or if we apply some force, that doesn't change its physics.
Right. The key is that if you do something to the system, like shifting it in time, moving it in space, or rotating it, and the fundamental physics remains exactly the same, no preferred direction, no preferred time, then a conservation law pops out. If you add a force or break that symmetry, like having gravity pulling down, then that symmetry is gone, and so is the related conserved quantity. So Noether's theorem is all about how those symmetries or their absence shape what stays constant in a system.
So, what about this quantum mechanics example you gave, like a particle in a spherically symmetric potential, that is the hydrogen atom? So, if We are not applying any external field or something interaction with the hydrogen atom. So hydrogen atom is happy with their own Coulomb potential and all those quantum number and the spherically symmetric potential will.
Exactly. In the hydrogen atom, the electron feels the Coulomb potential from the proton, and that potential is spherically symmetric. No direction is special. Because of that symmetry, angular momentum is conserved. Each quantum number, like the azimuthal quantum number tied to angular momentum, comes out of that. Now, if you add something like a magnetic field, that symmetry breaks, and those neat quantum numbers shift. But in that untouched symmetric case, the hydrogen atom's happiness is reflected in those conserved quantities.
Okay, give another intuition. How can we observe directly the symmetric picture in this hydrogen atom case? And when do we not observe that symmetry?
You can directly observe the symmetry of the hydrogen atom when you look at its energy levels. In that ideal isolated hydrogen atom, the energy levels only depend on the principal quantum number. But if you bring in an external field, like the Zeeman effect with a magnetic field or the Stark effect with an electric field, the symmetry breaks. Suddenly, direction matters, and those once degenerate energy levels split. So symmetry is like a perfect balance. When nothing external distorts it, you see neat, simple patterns. When you poke it with external influences, that balance is broken, and that's when things shift.
But you mentioned about the definition of symmetry is like bridging between Noether theorem definition is bridging between symmetries and the conservation laws. So if your system behaves the same way under some transformation, say it looks like identical if you shift in time or rotate in its space, then you get a conserved quantity, time symmetry, or you get energy conservation, spatial symmetry, momentum conservation. So, and you in the hydrogen atom case or the particle case, you mentioned about that if the hydrogen atom is not interacting with anything, then we can observe the symmetry. That two things is bit tricky to me to understand the core idea.
I get it. Let me tie them together more intuitively. Think of symmetry as a rule. If the system doesn't care when you look at it, time symmetry, it rewards you with energy conservation. If it doesn't care where you look, space symmetry, you get momentum conservation. In the hydrogen atom, when there's no outside influence, it doesn't care which direction you look, so angular momentum is conserved. But the moment you apply something external, like a magnetic field, now the atom cares about direction, breaking that symmetry. So Noether's theorem is like a bridge between these cares, symmetries, and the treasures they give us, conservation laws.
Oh, thank you.